Properties of indefinite integrals. In the previous sections, we established that integration is the inverse process of differentiation. Remember how we talked about derivatives, finding the rate of change of a function? Well, integration is essentially the reverse of that. It's about finding the original function given its rate of change. Think of it like this. If differentiation takes you down a hill, integration takes you up that same hill. To solve complex integration problems efficiently, we do not always rely on the method of inspection. Now, we can sometimes guess the integral, what we call integration by inspection, but that only works for very simple cases. As problems get more complicated, just guessing isn't a reliable strategy. It's like trying to solve a puzzle without a plan. Instead, we use a set of algebraic and operational properties. That's where these properties come in. These are like the tools in our integration toolkit. They give us a systematic way to approach problems, even the tricky ones. These properties allow us to break down a complicated integrand into simpler parts that can be integrated using standard formulae. What this means is, instead of trying to integrate a huge, messy function all at once, we can use these properties to split it up into smaller pieces that we already know how to integrate, using the formulas we've learned. This makes the whole process much more manageable. Okay, so let's move on to discussing how we actually solve integration problems. In the upcoming slides, we'll be diving into these properties one by one, showing you exactly how to use them. So, pay close attention, as mastering these will be key to becoming proficient in integration. The inverse relationship. Okay, so let's move on to slide 2. As we discussed on the previous slide, we're exploring the properties of indefinite integrals, ways to manipulate and solve integration problems more efficiently. The core idea here is understanding how integration and differentiation relate to each other. Essentially, integration and differentiation are inverse operations. Think of it like squaring a number and then taking its square root. If you do both, you end up back where you started. The same principle applies here. Applying differentiation after integration or integration after differentiation will generally bring you back to your original function. Now let's look at this a bit more formally. We have two key points here, labeled A and B. A differentiation of an integral. This part states that if you first integrate a function, let's call it f of x, and then differentiate the result, you'll get back the original function f of x. Mathematically, this is written as d by dx of the integral of f of x dx equals f of x. So the d by dx represents the derivative with respect to x. The integral symbol is, well, the integral f of x dx is the integral of the function f of x. And the result is simply f of x. It's like the integration and differentiation cancel each other out. B integration of a derivative. This is similar, but with the order reversed. If you first differentiate a function f of x and then integrate the result, you also get back the original function f of x. However, there's a crucial difference here. We need to add a constant of integration, which we denote as c. Why? Because remember, the derivative of any constant is 0. So when we integrate, we lose information about any constant term that might have been present in the original function. Therefore, we add c to represent that lost constant. Mathematically, this is expressed as the integral of f prime of x dx equals f of x plus c. F prime of x represents the derivative of f of x. Let's solidify this with an example. Let's say our original function, f of x, is x cubed. Step 1, we find the derivative of f of x. The derivative of x cubed is 3x squared. Step 2, now we integrate this derivative, 3x squared. So, we have the integral of 3x squared dx. We can pull the constant 3 outside the integral, giving us 3 times the integral of x squared dx. Using the power rule for integration, the integral of x squared is x cubed divided by 3. So, we have 3 times x cubed divided by 3, which simplifies to x cubed. And crucially, we must add the constant of integration, c. Therefore, the final result is x cubed plus c. As you can see, we've successfully returned to our original function, x cubed, demonstrating the inverse relationship between integration and differentiation, and the importance of that constant of integration, c. This understanding is fundamental as we move forward and explore more complex properties of indefinite integrals on the next slides. Equivalence of indefinite integrals. Okay, let's move on to slide 3, where we discuss the equivalence of indefinite integrals. Now, remember from the previous slides, we've established that integration and differentiation are inverse operations, and that indefinite integrals always include a constant of integration, c. This concept of equivalence builds directly on that. So, the slide starts by stating that two indefinite integrals are considered equivalent if they represent the same family of curves. What does that mean? Well, think about it this way. If you have two indefinite integrals, they're equivalent if their results are identical except for a constant value. In simpler terms, two integrals are equivalent if their results differ only by a constant. This is crucial because the constant, c, represents an infinite number of possible vertical shifts of the same basic function. Now, let's look at the concept section. It states that if the integral of a function f of x is equal to g of x plus c1, and also equal to h of x plus c2, then g of x and h of x must differ by a constant, specifically c2 minus c1. Let me explain that a bit further. Because integration reverses differentiation, any two functions that have the same derivative must be parallel to each other, meaning they have the same slope at every point, but they can be shifted vertically. That vertical shift is represented by the difference in their constants of integration. So, if two integrals give you different functions, g of x and h of x, but they both come from integrating the same original function f of x, then those functions must be the same shape, just potentially shifted up or down. Let's illustrate this with an example. Consider the integral of cosine x. You might find the answer to be sine x plus c. However, another perfectly valid answer is cosine of pi over 2 minus x plus c. Now you might be wondering, aren't those different functions? Well, they are, but they are mathematically equivalent. This is because sine x is actually equal to cosine of pi over 2 minus x. They represent the same family of curves, just expressed in a different way. Both answers are correct, and both will give you the same derivative, which is negative sine x. This is important as we move forward, especially when we start applying the properties like the sum rule and constant multiple rule on the next slides. Remember, there's often more than one way to express the correct indefinite integral, as long as they differ only by a constant. The sum rule. This slide introduces the sum rule. Essentially, this rule allows us to integrate expressions that are sums of multiple terms, think polynomials like x squared plus something else, or combinations of trigonometric functions. It lets us break down a more complex integral into simpler parts that we can handle individually. Here's the formula. Integral of f of x plus g of x with respect to x is equal to the integral of f of x with respect to x, plus the integral of g of x with respect to x, so we're simply saying that the integral of a sum is the sum of the integrals. Let's see this in action with an example. We want to find the integral of x squared plus sine of x with respect to x. Step 1, we apply the sum rule. This means we split the integral into two separate integrals, the integral of x squared with respect to x plus the integral of sine of x with respect to x. Step 2, now let's integrate the first term, x squared. Remember the power rule for integration? We increase the power by 1, so 2 plus 1 is 3, and then divide by the new power. That gives us x to the power of 3 divided by 3. Step 3, next, we integrate the second term, sine of x, from our standard integral formulas. We know that the integral of sine of x is negative cosine of x. Step 4, finally, we combine the results of integrating both terms. So, we have x cubed divided by 3 minus cosine of x, and crucially, don't forget to add the constant of integration. See, so, the integral of x squared plus sine of x is x cubed divided by 3 minus cosine of x. Plus, see, this sum rule will be incredibly useful as we tackle more complex integrals, especially those involving polynomials, as you'll often need to integrate each term separately. In the next slide, we'll look at another helpful property, the constant multiple rule, which builds on these ideas. Okay, let's move on to our next property of indefinite integrals. As we discussed earlier, sometimes we need to use properties to make integration easier, rather than just guessing the integral directly. The constant multiple rule. Essentially, if you have a function multiplied by a constant, a simple real number, let's call it k, you can actually pull that constant outside of the integral sign. This is a really helpful simplification technique. It allows you to focus on integrating just the variable part of the function, which often makes things much easier. Let me show you the formula. We write it as the integral of k times f of x with respect to x is equal to k times the integral of f of x with respect to x. Remember, k represents that constant real number. To help you understand why this works, let's consider a real-world analogy. Imagine you're tasked with calculating the total area of 5 identical rectangular plots of land. You could calculate the area of each plot individually and then add all 5 areas together. But a much simpler approach would be to calculate the area of just one plot and then multiply that result by 5. The principle is the same with this constant multiple rule. We're just scaling the integral. Now, let's walk through a step-by-step example. We want to find the integral of 7 times e to the power of x with respect to x. Step 1, identify the constant. In this case, our constant k is equal to 7. Step 2, apply the rule and move the constant outside the integral sign. So, we rewrite the integral as 7 times the integral of e to the power of x with respect to x. Step 3, now we integrate the remaining function, which is just e to the power of x. We know from our basic integral formulas that the integral of e to the power of x is simply e to the power of x, so we have 7 times e to the power of x. Step 4, and finally, don't forget to add the constant of integration, c. Therefore, the final result is 7 times e to the power of x plus c. Okay, so let's move on to another useful property of indefinite integrals. As we've discussed, we're learning ways to make integration easier, rather than always relying on finding integrals by inspection. Now, this slide introduces the constant multiple rule. This rule, like the ones we've seen before, will be incredibly useful as we tackle more complex integration problems. In the next slide, we'll build on these ideas and look at how to integrate even more complicated functions using the concept of linearity. Linearity. It allows us to integrate a linear combination of multiple functions simultaneously. Now, what does that mean? A linear combination simply means we have several functions each multiplied by a constant and then added together. Let's look at the formula. We have the integral of k1 f1 of x plus k2 f2 of x, and so on up to kn fn of x, with respect to x. This is equivalent to k1 times the integral of f1 of x, plus k2 times the integral of f2 of x, and so on up to kn times the integral of fn of x. In simpler terms, we can pull out any constant multipliers and then integrate each function separately, and finally combine the results. This is incredibly useful when dealing with polynomials or any expression that's a sum of terms. Now, let's work through a step-by-step example to solidify this concept. We want to find the integral of 4x cubed minus 6x squared plus 2 with respect to x. Step 1, use the linearity property to split the integral into 3 parts. So, we rewrite this as 4 times the integral of x cubed dx minus 6 times the integral of x squared dx plus 2 times the integral of 1 dx. Notice how we've distributed the integral across each term. Step 2, integrate each term individually. Let's start with the first term, 4 times the integral of x cubed dx. Using the power rule, the integral of x cubed is x to the power of 4 divided by 4. Multiplying that by 4, we get x to the power of 4. Next, we have minus 6 times the integral of x squared dx. Again, using the power rule, the integral of x squared is x cubed divided by 3. Multiplying that by -6, we get -2x cubed. Finally, we have plus 2 times the integral of 1 dx. The integral of 1 with respect to x is simply x. Multiplying that by 2, we get plus 2x. Step 3, combine the terms and don't forget to add the constant of integration, c. So, our final result is x to the power of 4 minus 2x cubed plus 2x plus c. And that's it. We've successfully integrated a polynomial using the linearity property. Remember, this property builds on the sum rule and the constant multiple rule, giving us a powerful tool for tackling more complex integration problems. In the next slide, we'll discuss some common mistakes to avoid, so you can ensure you're applying these properties correctly. Okay, let's move on to our next property, linearity. As we've seen with the sum rule and the constant multiple rule, integration offers us ways to simplify complex problems. Linearity essentially combines these two rules into one powerful property. Common mistakes to avoid. Okay, let's move on to slide 7, where we discuss some common mistakes students make when working with indefinite integrals. It's good to be aware of these before you encounter them in your problems, so you can avoid losing marks unnecessarily. 1. The product trap. A very frequent mistake is incorrectly assuming that the integral of a product of functions is simply the product of their individual integrals. Let me write it out. The integral of f of x times g of x with respect to x is not equal to the integral of f of x with respect to x, multiplied by the integral of g of x with respect to x. Remember, integration doesn't distribute like that. The rules we've learned, like the sum rule, only apply to addition and subtraction within the integral, not to multiplication. You can't just separate out the integral of each part when they're multiplied together. This is a really important point to remember. 2. Forgetting the constant. This is a classic. Students often forget to add plus c, the constant of integration, at the end of the integration process. Now, we've discussed this before, but it's worth repeating. Remember that an indefinite integral doesn't give you a single function, it gives you a family of functions. The derivative of any constant is 0, so when we reverse that process with integration, we need to account for all possible constants. Plus c represents that entire family of functions that have the same derivative, so always include plus c in your indefinite integral answers. 3 constants in the denominator. Sometimes you'll see an integral where a constant is in the denominator. For example, the integral of 1/5 times f of x. With respect to x, don't let that throw you off. That constant is still just a constant multiple. In this case, k equals 1/5. And, as we learned with the constant multiple rule, you can move that constant outside the integral sign. So, you'd rewrite it as 1/5 times the integral of f of x. With respect to x, it's a subtle point, but it can save you from unnecessary complications. Alright, so keep these 3 common pitfalls in mind as you practice. Now, let's move on to the final slide, where we'll recap the key takeaways from this entire section. Key takeaways. Okay, let's recap everything we've covered regarding the properties of indefinite integrals. This is slide 8, and it's designed to solidify the key takeaways from our discussion. First, and most fundamentally, we have the inverse nature of integration and differentiation. Remember, we started by establishing that integration is essentially the reverse process of differentiation. So, if you differentiate an integral, you get back to your original function, and vice versa, they undo each other. This is the bedrock of everything we've been doing. Next, let's talk about equivalence. When we're dealing with indefinite integrals, there isn't just one right answer. There is a family of correct answers. 2 indefinite integrals are considered equivalent if they differ only by a constant. This is because the derivative of a constant is always 0, so adding or subtracting a constant doesn't change the slope of the function, only its vertical position. Now, let's move on to the rules that help us solve these integrals. The first is the sum rule. This rule states that the integral of a sum of functions is equal to the sum of the integrals of those functions. Mathematically, this is represented as integral of f plus g is equal to the integral of f Plus, the integral of g. This is incredibly useful when you have polynomials or combinations of trigonometric functions inside your integral. It allows you to break down the problem into smaller, more manageable parts. Following that, we have the constant multiple rule. This one's pretty straightforward. If you have a constant multiplied by a function inside the integral, you can simply pull that constant outside the integral sign. So, the integral of k times f is equal to k times the integral of f, where k is just a constant number. Think of it like factoring. It simplifies things without changing the result. We saw a real-world analogy on the previous slide to help illustrate this. Finally, we have linearity. This is really just a combination of the sum rule and the constant multiple rule. It allows us to integrate a linear combination, meaning a sum of constant multiples, of multiple functions all at once. So, the integral of k1 times f1 plus k2 times f2, and so on up to kn times fn, is equal to k1 times the integral of f1, plus k2 times the integral of f2, and so on, up to kn times the integral of fn. This is a powerful tool for tackling more complex integrals, like those involving polynomials with multiple terms. These 5 key takeaways are the foundation for mastering indefinite integration. Make sure you understand each one, as we'll be building on these concepts in future lessons. Are there any of these points you'd like me to revisit or explain in more detail?